I'd like to talk about temperature, the property temperature. And what do you know about temperature? Well, this is a thermometer that I've had since I got my first apartment in Blacksburg as an undergraduate. So I hope you're familiar with this. This would be let's see, it's an alcohol, red dyed alcohol in a glass tube and calibrated in degrees F and degrees C. So down in the basement here today, looks like we're looking at about, gosh, about that looks like about 24 degrees C or 76, about 76 degrees F. So it's warmed up a little bit in the basement since this morning. But anyway, I think I'll bet everybody knows. Well, this is a very traditional and old school way of measuring temperature. So let's get started and talk about some of the details you'll need to know to get good at this property in thermodynamics class. So let's apply a little common sense 101 to get started in talking about section 1.7 called temperature. And I'm going to suggest that your life's experience so far, it really gives you a good feel for what is temperature. And, if we had a little discussion, you'd say, well, it's all kind of based on a feeling. By golly, um, I might not know the physics description of what temperature is, but I know when I'm hot and I know when I'm cold. And textbook section 1.7 is a pretty good read for some backgrounds about some of the subtle aspects of temperature measurement. So let's see, here it'd be, now this particular thermometer, this wall thermometer, that's going to be some type of bimetallic strip or something, but it's also indicating temperature, isn't it? Temperature is an intensive property. And what I want to do in this module is help you quickly get comfortable with working with all four temperature unit types. And also going to remind you and get you familiar, hopefully comfortable to understand that working in absolute temperature is going to be extraordinarily important for your success in this class. And I suspect you have an understanding or maybe a rough understanding of the difference between sort of a regular temperature, degrees F and degrees C, versus absolute temperature. So we'll go through some details. The other thing is measuring temperature. So I've shown three screenshots of three types of thermometers. Of course, the one on the right, of course, is this alcohol in a glass tube. It's a sealed glass tube, and you know how it works, don't you? The hotter it gets, this bulb of red alcohol, it's going to tend to expand. So as the temperature goes up in the room, the alcohol expands, and that's what shoves the liquid level up into the tube. And that's what gives you your reading for temperature. I guess the one in the middle, sort of this dial indicator, that would be a bimetal strip, wouldn't it? A bimetal strip that's wound around and around. And so as the temperature increases or decreases, the bimetal strip is going to move and give you temperature indication. And it's certainly in the common world now. So here, this would be an oven thermometer. You're going to stick this probe in the oven, and then you'll have the indicator outside the oven, and there's going to be some type of thermocouple probe, which would be a probe again that's connected and soldered together with two different types of metal wires, and then electronically, then we can relate sort of a voltage to a temperature. And here it's showing you what the temperature is in the oven. Okay, and so all three of these have something in common, and that is thermal equilibrium. And so let's see, I see that it says go live, so I'm going to quit sharing, and I'm going to go back live. And so you clearly see that the temperature indicator is not moving. It's not going anywhere. It just says, look, we're at 76 degrees F here in the room. The reason is that this bulb this bulb full of red alcohol, it's in thermal equilibrium with the room. So that's why things aren't going anywhere. There's a balance, a thermal balance. There's no heat transfer between this little area here and the rest of the room. So I'm going to try to do a little demo. I have not practiced on this. So I've brought in this is a space heater, and I'm going to turn the space heater on, and it's going to be kind of loud. And I don't know if Zoom is going to pick it up or not. But what I'd like to try to do is hold the thermometer up here. Oh, good. Okay. And then let's both watch to see what happens to the temperature indication when I turn the heater on. And so I can feel the heat, the hot air coming from the space heater. Wow. And look at this. So already, wow, this so it's blowing air over top of both the metal backing and the bulb. And look at this. We're already up. I don't know if we're ever going to get to steady state, but you can see the alcohol in the thermometer climbing and climbing and climbing. And you see that, eventually, if I could hold this thermometer still enough, we would get to a point, and let's say we're at that point right now, just to save time. Oh, it's still climbing, isn't it? But you get the idea that this bulb is not in thermal equilibrium yet with the hot air flow. And I don't want to I don't want to blow up my thermometer here, so I'm going to quit my experiment. And wow, that metal thermometer base is pretty hot to the touch now, so it's probably more than, but you get the idea. You get the idea of how a thermometer works and how it would indicate temperature, right? Okay. Some familiar temperatures and conversions that I hope you already are familiar with. Let's go through some mental exercises. So do you know off the top of your head, could you say what the boiling point of water in New York City is in degrees F and also in degrees C? Well, I've got the answer sitting there in front of you, but if you hadn't looked at the answer yet, be honest with yourself. If New York City is about at sea level, of course. And does it come to your mind that boiling water in New York City would have a temperature of about 212 degrees F or about 100 degrees C? That would kind of make sense to you, wouldn't it? Okay. Let's go to Blacksburg and think about wintertime. And at what point will water freeze in Blacksburg? Did 32 degrees F come to your mind? And how about 0 degrees C? So those two would be the freezing point or the ice point of water in Blacksburg or New York City or really just about anywhere on Earth. So here's another question. And we just went through the exercise of actually reading off the temperature here with the thermometer. But if the temperature in the room is 78 degrees F, about what would you expect the temperature to be in degrees C? And I'm hoping that you would say, oh, 78 degrees. I know I can do the math given enough time, but I sort of have a feel for it that would be about 25 degrees C. It's my hope that you've got all three of these sort of in your head just as a result of your experience so far. Okay, now back to thermoclass. And it's my hope that you can get these conversions into your head. And I'm going to try to give you some tips on how to get the conversion into your head and how it helps me. I don't write these formulas down on a sheet of paper. I don't have a formula sheet. Okay. But I'm going to show you that if you know the boiling point of water and you know the freezing point of water, and you don't have these written down, you can derive these two relationships. Changing degrees C to degrees F. So I do have to remember 9/5. If I take 9/5 of a boiling point, let's look at the boiling point. I know it's 100 degrees, so 9/5 is 1.8. So if I take 9/5 of 100 and add 32 to it, I'm going to get 212. That's the way I remember the conversion from degrees C to degrees F by the boiling point. Okay. Okay, how about degrees F to degrees C? And so let's look at the freezing point. If I take, oh, I'm sorry, forget the freezing point. So, gosh, I had a mental lapse there. I want to go from degrees F to degrees C. I'm still going to use the boiling point, so just forgive me for talking about the freezing point. How do I get degrees F to degrees C? I know the boiling point, it's 212 degrees F. I've got to subtract 32 from that, okay, because that's the freezing point, isn't it? Take 32 away from the boiling point, okay, that's 180. If I multiply that by 5/9, that's 100. And so my formula, gosh, this was terribly explained, wasn't it? But let's keep blundering through. Gosh, whew, terrible. Degrees F, that's 212. The boiling point is 212. I got to subtract the freezing point from it, 32. If I subtract the freezing point from the boiling point of degrees F and multiply that by 5/9, I get degrees C. Okay, and so that's sort of my trick, terribly explained, that hopefully you could get this derivation and put it down quickly on a quiz or a test, even if you had not written it down on a formula sheet, if you're allowed to have it. So please forgive me for that terrible explanation. Okay, now to something that's a little simpler. And I want to suggest that you really, really need to get this in your head without writing this on a formula sheet from college chemistry. Changing degrees C to absolute temperature, degrees K. Maybe even in high school chemistry, you've got this. You simply add 273 to degrees C to get degrees Kelvin. So that one's pretty easy because a lot of folks have a lot of practice with that. A little tougher in the degrees Fahrenheit and the absolute temperature in the English system of units. And that's called the Rankine scale, degrees Rankine, degrees R. So this is one you might spend a little time committing to memory. Simply add the number 460 to degrees F to get degrees R. I did not know this one until I took my first class in thermodynamics in 1973. So I've got it now. It didn't take me long to get it. Add 460 to degrees F to get degrees R, Rankine. So in thermodynamics class, you're nearly always want to be working with temperatures in the absolute temperature scales, either degrees K or degrees R. Okay, here's our recap. I now declare you experts in the measurement of temperature. So temperature is an intensive property. You remember why? Okay. If you could take a little sample, if you can get into a closed system and you could sample a lot of subsystems within that major system, do you see that you would measure within that thermodynamic system, the temperature would be the same throughout that system. Using absolute temperatures is going to be critical for success in this class. And despite my terrible explanation of converting degrees F to degrees C and vice versa, remember, you have to know the freezing point and the boiling point to be able to derive those relationships out of thin air. A capable engineer has to be able to quickly convert degrees F to degrees C or degrees C to degrees F. So those are the three takeaways. I hope you got some enjoyment and maybe a little better understanding of the way we measure temperature here in practical applications. Next video is all about energy. Going to give you an introduction into what, for a thermodynamics class, what are we going to define energy as? And we're going to talk about intensive and extensive properties as it relates to energy. So I hope that helps with respect to temperature. Sorry about my terrible explanation about degrees F to degrees C conversions.